Woohoo! We're live! This is Math 75, Mathematical Analysis for Business, and this is 9.4, and we are doing calculus! Yay, calculus! And this is the portion of the section where we're going to use work on the applications. So the really important thing is, if you haven't practiced yet, you probably want to hold off on this video, go practice, go to the homework and practice taking derivatives, and then come back when you're done with that, when you feel really comfortable with taking derivatives. So here we go. Now, the problem with the way that I'm going to be presenting this is that it's going to feel kind of silly, in that the answer to every single question I will ask is take a derivative. So the bigger question is when you're out in the big wide world, how will you know you're supposed to take a derivative to solve a problem? And so that's what we're going to focus on here. So you are given, and it doesn't, if you read quickly through this, we are not given any context. So capital P of X equals 3x squared minus 6. We know nothing. We know, well, we know a little bit. We know that this is a quadratic, right? This is a smiley face parabola, which is really lovely. And we're asked a bunch of questions about it. So let's take a look at what the questions are. First one. What is the instantaneous rate of change? And I'm going to stop right there and underline this. And if you see the phrase instantaneous rate of change, that means derivative. Yay, everything's going to mean derivative here. This is kind of like if I were, you know, your English teacher and we were reading through math poetry, and I'd say, oh, the author is talking about derivatives. And you'd be saying, well, I thought they were talking about their dog. And I'd be saying, no, the deeper point is derivatives. So what is the instantaneous rate of change of P of X at any point X? That means we want the derivative of P at X. So the general form. So let's take a look. If P of X is 3x squared minus 6, first we got to take the derivative of 3x squared. So 3 hangs out, the 2 comes down, and you subtract 1. And then minus, and what's the derivative of a constant? You're right, the derivative of a constant is 0. So P prime of X equals 6x minus 0. Ooh, not too bad. Woohoo. Okay, so this is our instantaneous rate of change at any point X. Let's go on to B. What is the instantaneous rate of change of P of X at X equals 5? Well, again, I'm going to say, oh, what a surprise. In a chapter about taking the derivative, it asks you to take a derivative. But again, you want to look for that. That phrase is instantaneous rate of change. And remember, we talked about rates of change a couple sections ago. So the average rate of change was that this line segment we drew between the points, and instantaneous is what happened when we moved the points together. So it's the derivative, and we want to find X equals 5. So we'll say P prime of 5 equals 6 times 5 equals 30. So remember when we were working on this before, and I was talking about how when you're looking at a particular graph, the derivative will be different in different parts of the graph. So sorry about talking slowly. I was trying to get this set up. So if I've got my original P of X is 3x squared minus 6. Okay, and let's see, what do I want to do? I want to set that. I want to look from -1 to +10, and y is going to be from -6 to 100. Okay, so Let me move this away from where. Oh, that ring light. It's oh so professional, but yet oh so reflecty. Okay. So here we go. I don't know if you guys can see this little tiny number down here. This is 5. And where is my little tiny, I have lost my little tiny ruler. Oh, quel dommage. Oh, ruler, we will miss you. We're going to use chopstick, hashi. Ready to make a new, I keep a bunch of these. We have to go out and eat takeout every now and again so I can make more puppets. So when x equals 5, we're right there. So if you look at this, the derivative, remember, is the slope of the tangent line at that point. Now, is the tangent line always like that? And the answer is no. Sometimes, like if you look down there at the middle, right there at the vertex, the tangent line is horizontal. If you look over here where x is negative, the tangent line is decreasing. It's going down. The slope is negative. So we've got a lot of different possible derivatives or slopes. And so that's why it's interesting to ask, where's my pen? What is the instantaneous rate of change of p of x at x equals 5? So when x equals 5, we're at 30. And that's it. In this case, there's no, for this application, we're not told anything more. So there are no units. It's just a number. So it's just the number 30. Okay. What is the slope of the tangent to p of x at x equals 5? And again, I'm going to draw a little poorly drawn graph. Remember, it looked a little bit like this. And if this is x equals 5, then this is the tangent. And the slope of the tangent equals the derivative. So it's asking us for the derivative. Slope of the tangent means derivative. Like I said, everything means the derivative. When you're a math teacher, you go out and you see derivatives everywhere. So what's the instantaneous rate of change? 30. What's the slope of the tangent at x equals 5? 30. Last question. What is the equation of the tangent line at x equals 5? Now, this is an interesting question. So we know the slope. The slope of the tangent line is the derivative, so that's 30. But then where do we get the point? And the answer is, to find the point, we know that x equals 5. Now here's the thing. Remember, when we plug in 5 to the derivative, we get the slope. If we want to find the y value, we have to go back up here to the original. P of 5 is 3 times 5 squared minus 6, which is 3 times 25 minus 6, which is 75 minus 6, which is, what is that? That's 69. Okay. Oops, sorry, got too short for that. Okay, so we have, the slope is 30. And our point is the point 5 comma 69. And then again, you can use whatever method you like. I tend to use the point slope form, but you could also use the slope intercept. And since the last time I used point slope, let me use slope intercept. I'll just show you that one. The y equals mx plus b, right? You could do that, or you could do the y minus y1 equals m times the quantity x minus x1, that one. But let's go ahead and try this one. So this format, I would plug in the 69 for y, 30 for the slope, 5 for x, oops, and not equals, oh my goodness. Like I said, fine balance between caffeine and exhaustion, plus b. Okay, so 69 equals 150 plus b, minus 150, minus 150. And then I get, what is that? Oh my goodness, I can't do this. So it's 100 minus 19. So I think this is negative 81 equals B. Does that make sense? I believe so. I'm doing it on live video, so hopefully I haven't totally messed it up. So let's come here, and then we come down there. So then we get y equals, again, the slope is 30. B is minus 81. So that's the equation of the tangent line. Let's come back. And again, I'm just using Desmos, but you can use whatever graphing app. Google, you can just Google a graph. There are lots of ways to graph it. And what I'm going to do is I'm going to type in as my second graph 30x minus 81. Ooh, isn't that pretty? Look at that. Oh, it's a little bit harder to see. Let's see, negative. Nope. Negative 6 to 6, negative 6 to 100. Okay. So can you guys see there is a blue line? That's the tangent line. And here's our original function. And they intersect at right there at x equals 5. That's the point of tangency. That's where the line, the tangent line, bumps up against the function. And we talked about it before. The tangent line is a really nice approximation for the function right there near the point of tangency. And obviously, as you go further away, a line is not going to describe a parabola very well. But it tries. It does its best. We're like, you know what? That was a solid, solid attempt. Thank you so much, line, for being so helpful. Okay, shall we do some more? Spoilers, it's going to be the derivative. Seriously, it's like if you were doing a murder mystery in calculus, the answer would be, who did it? The derivative. Okay, the derivatives and marginal analysis. Oh, I got to stop talking so much. We got 2 more pages. Okay, the total revenue in dollars for a commodity is described by the function, and you know me, I'm going to rewrite it so it's a little bit bigger. R of x, so that's revenue, equals 300x minus 0.02x squared. Okay, then what is the marginal revenue? And I'm going to underline it in yellow, and I'm going to give you 3 guesses, and the first 2 don't count. What do you think we're going to do to find the marginal revenue? You're right. Sorry, you're you. How do I do that? It's like I'm pointing right at you. Anyway, so the marginal revenue, derivative. Yay! So if R of x equals 300x minus 0.02x squared, what's the derivative? So we need to find the derivative in general. So remember 300 times x. If it's just an x, then you're left with the 300. The x goes away. You take the derivative. This one's a little harder. You got to do a little work. The 2 comes down. 2x to the 2 minus 1. So you get 300 minus, and this becomes 0.04, and it's x. And we can take a moment and talk about why bother with derivatives. Well, derivatives are really great because, 1, they help us forecast things. And you might ask, but wait a minute. If we know the equation, if we know the function, we can just graph it. We don't need to forecast it. And so here I'm going to let you in on something, and that is that we're doing really much simpler problems than calculus is actually designed for. We're just working with very simple, right now they're quadratics. They're not really complicated, so of course we could totally graph it. But what I can show you is that when we take the derivative, notice how everything gets a little bit easier? A lot of times the derivative is actually easier to work with than the original function. So we work with the derivative and just look at what it tells us rather than going to all the trouble of the original. So that's one reason we're going to use it. Now, in this case, it doesn't say in general for all x, it says when 40 units. So we want the derivative at 40. So that's 300 minus 0.04 times 40. You know I'm too sleepy to do that. I'm sure it has something to do with 16, right? 40 and 4. So I got 300 minus 0.04 times 40. And I get 298.4. Now, total revenue, this is actually an application that's set with units. This is in dollars. So we've got $298.40. Remember that dollars are, we count them with 2 digits to the right of the decimal point. Or if you're in another country, a comma. United States flips that. We use decimal points instead of commas and vice versa. So what does your answer to part A mean for the 41st unit? And at which point you guys are going, what are you even talking about? And the answer is the marginal revenue tells you it is an approximation So $298.40 is an approximation for the revenue obtained by producing and selling the 41st unit. Now, don't necessarily memorize that. I'm not necessarily the best one at writing these down. There are a lot of ways to phrase it. But basically, if I calculate R of 41, so let's see, this is the original. So we're going to go back to the original, 300 times 41. And I know some of you are like, what are you even doing? Why are you suddenly going on without explaining this? And the answer is, if I do this, then I can explain this. So R of 41, which is plugging in 41. This one I'm really not going to do in my head. So it's 300 times 41 minus 0.02 times 41 squared. Let's hope the calculator can handle this. Equals 12,266.38. $12,266.38 is the revenue from the first 41 units. When we calculate revenue, it gives us the total revenue, all of the revenue together, all of it. So if I want to know just the 41st unit, what I have to do is I have to find all the revenue for the 41st. And then I have to find all the revenue to the 40th. Okay, already I'm annoyed at how much work this is. Uh-oh. Sorry, I kind of careened into the last one. So 300 times 40 minus 0.02 times 40 squared. And that's equal to 11968. Okay. Revenue from first 40 units. And then what I do is I take R of 41 and I subtract R of 40, and that will just give me the 41st one. Does that make sense? So if I want to find, if I've got 5 things, and I know the sum of the 5 things, but I want to know just the 5th thing, what I do is I figure out the sum of the first 5, and then I figure out how much the first 4 are, and I subtract them, and that leaves me with the 5th one. 41 of them minus 40 of them is just that last 41st one. So that's going to be $12,266.38 minus $11,968. And so that's 12,266.38 minus 11968 equals $298.38. So what are we doing? What is marginal analysis? Well, basically, marginal analysis is you're never going to come into a business, except for the very beginning of the business. You're never going to come into a business right when it starts. Most of the time when you're looking at a business, it's already operating. It's already made. It's making 40 burritos. These are very expensive burritos. It's making 40 rocking chairs. It's making 40 whatever. And your question as the potential CEO or as a manager or as whoever you're going to be in that company, perhaps the sole proprietor, your decision is, should you make more? Should you try to sell more or should you just stay where you are? And there are a lot of considerations to this. But one of the ways to look at it is something called marginal analysis. We're going to look at the margin. And so what we're going to look at is if you're at 40 and you're making this much, if you make one more, you could make an additional just under $300. And so you could say, okay, my revenue would be around 300. And then what you could do is you could look at your marginal costs, see what would the cost be of just one more, and you compare. See what your marginal profit would be. So a lot of times companies use marginal analysis, and hopefully you'll use it in other business classes to figure out, should you increase capacity? Should you increase production? However, can we agree that this was a big pain? This was blah. I don't want to have to do this. How hard was this though? Easy peasy. How close were we? Awfully dang close. Do you see? This is an approximation. So I said 298.40. This is 298.38. That's pretty close. So this very quickly gave me a really nice approximation. Could I have done this? Absolutely. But this takes more work. And you can imagine if I said, okay, now imagine a much more complicated formula, this part could take a long time. This is just a single calculation. This is 2 or 3 or 5 or a million. And so this is a quick and dirty way to just do it and be done. Okay, that's what marginal analysis is. What do you need to know? Here's what you need to know. Someone says find marginal anything. Take the derivative, differentiate. If it says at a certain number of units, plug it in. If they say, what is the actual additional revenue or the actual additional profit or actual additional cost, then you have to calculate the unit you're interested in and one fewer. So 41st minus 40. Okay, so let's go on to the last page of this section. Woohoo! Okay, this is a cost function. So very similar, except it's easier to spell. Here's our cost function. This has gotten that escalated quickly. Our cost is negative 0.1 times x squared plus 25x plus 10. Okay, so I want to find C of 10. So C of 10 is, let's see, negative 0.1 times 10 squared plus 25 times 10 plus 10. Oh my goodness. Okay, so clear negative 0.1 times 10 squared plus 25 times 10 plus 10. Pretty cool, huh? You were wondering whether I'd ever remember that there's a squared key. I did. Okay. So it's 250. So what is this number? The cost to produce the first 10 units is $250. And I think we're told it's a cost function. We're not told if it's dollars, so I'm just assuming. Okay, so Find the marginal cost function. Okay, marginal cost. Anytime someone says the word marginal from now on, ooh, derivative time. So let's find the derivative. First off, I've got negative 0.1, right? Because the negative 0.1 hangs out. Then the 2 comes down, and I get x to the 2 minus 1. Okay, that's the first term. Second term, I've got 25x, so what's the derivative of that? You got it, just 25. And what's the derivative of the constant 10? 0. Okay, so this is negative 0.2x plus 25. Okay, and that's c prime of x. Let's see if I can get a box around this guy. Woohoo. There we go. Find the marginal cost at x equals 10. The marginal cost is equal to the first derivative of the cost function. So at x equals 10, negative 0.2 times 10 plus 25. So that's going to be, I think it's going to be 23. Negative 0.2 times 10 plus 25. I don't trust myself, but yay, I got it. Okay, now we have to answer the questions. The awkwardly phrased questions. What does this mean? The sale of the next unit will blank total cost. So this is positive, right? So that means cost is increasing, right? The derivative is the slope. If the slope is positive, it's going up. So the sale of the next unit will increase because that's positive. If it were negative, it would decrease. Total cost by about $23. The sale of the next 2 units will increase total cost by about, and now here, this is a question where you could answer it a few different ways. But what I'm going to do for this one is I'm going to say you just multiply. So each unit, so if I make one more, the cost goes up 23. If I make up another one, the cost goes up 23. Make another one, 23. Now, how close am I when I start doing this? Do you remember what the rule was? Now this, let's turn this upside down. This is my quick and dirty way to get, because this parabola opens. Oops, sorry, you can't see that. This parabola opens downward. But remember what our rule, there we go. What our rule was, what happens the further you get from that point that you were interested in, the further away you get, the worse an approximation it is. So for the next 2 units, it's about $46 to make the next 2, but you're going to be a little bit off. And if you went for 3, that's going to be more off. So it depends on how approximately you want to get. Okay. Oh my goodness. Look at this. Look at this. We're almost there. Okay. Find C of 11 minus C of 10. Well, we already found C of 10, so let's find C of 11. Okay, so this is going to be -1 times 11 squared plus 25 times 11 plus 10 gives me did I do that correctly? Let me double check. 0.1, negative 0.1 times 11 squared is negative 12.1 plus 25 times 11 plus 10 There we go. I didn't do it correctly. Sorry, and you can't see it. So I got the answer 272.9. So what does that mean? The cost to make 11, the first 11 units would be $272.90. Now we've got the cost of the 10th unit is right here, was $250. That's from the first page. So then let's find C of 11 minus C of 10. 272.90 minus 250 equals, that looks like 22.90. This is, I'll come down here, the cost of the 11th unit. Okay, again, C of 11 is the cost of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 units. C of 10 is for the first 10. And so if we subtract them, we get the cost of the 11th unit. What was the marginal cost? The marginal cost was 23. The actual difference in price in cost was 22.90. See how close we were? That was pretty good. So if I guessed that in this very simple way, if I said if we want to make one more of this thing, it would cost us $23. I was pretty close, and I saved all this extra work. So that's the idea. It's just a quick way to approximate what's going on. Okay, you guys made it through an exceptionally long video. So give yourselves all a pat on the back. Yay, dance party. Dance party with my weird definition of the derivative. There we go, dance party. Okay, congratulations. Next up, we're gonna, for the next couple sections, we're just gonna learn lots of other techniques of differentiation, and we're gonna learn some more applications. So you guys are awesome. You're well on your way to being the smartest people you know. Woohoo. Math on, guys, math on.